Hosting someone like Kevin Murphy on your podcast is complicated. Not because Kevin himself is complicated. He's delightful, don't make me say what I didn't say, but because all the questions I had for him amounted to a 12-hour show. So, well, brace yourselves, folks. This is Learning Bayesian Statistics, episode 68, recorded August 16, 2022. No, stop that. I'm kidding, folks, of course. I didn't do that because, well, Kevin has a life, and this life started in Ireland, where he was born. He grew up in England and got his bachelor's degree from the University of Cambridge. After his PhD at UC Berkeley, he did a postdoc at MIT and was an associate professor of computer science and statistics at the University of British Columbia in Vancouver, Canada, from 2004 to 2012. And after getting tenure, he went to Google in California in 2011 on his sabbatical, and then, well, he ended up staying there. He currently runs a team of about 8 researchers inside of Google Brain, working on generative models, optimization, and other, as Kevin puts it, basic research topics in AI and ML. He has published over 125 papers in refereed conferences and journals, as well as 3 textbooks on machine learning, published in 2012, 2022, and the last one coming in 2023. You may be familiar, actually, with his 2012 book, as it was awarded the DeGroot Prize for Best Book in the field of statistical science. Outside of work, Kevin enjoys traveling, outdoor sports, especially tennis, snowboarding, and scuba diving. So, well, you could argue whether scuba diving is outdoors or indoors, but let's put that aside, okay, for a moment. And he also enjoys reading, cooking, and spending time with his family. This really is Learning Bayesian Statistics, episode 68, recorded August 16, 2022. Welcome to Learning Bayesian Statistics, a fortnightly podcast on Bayesian inference, the methods, the projects, and the people who make it possible. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. For any info about the podcast, learnbayesstats.com is la place to be. Show notes, becoming a corporate sponsor, supporting LBS on Patreon, unlocking Bayesian merch, everything is in there. That's learnbayesstats.com. If with all that info, a Bayesian model is still resisting you, or if you find my voice especially smooth and want me to come and teach Bayesian stats in your company, then reach out at alex.andorra@pymc-labs.io or book a call with me at learnbayesstats.com. Thanks a lot, folks, and best Bayesian wishes to you all.
Let me show you how to be a good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations.
What's a Bayesian? Is someone who cares about evidence and doesn't jump to assumptions based on intuitions and prejudice. A Bayesian makes predictions on the best available info and adjusts the probability, cause every belief is provisional. And when I kick a flow, mostly I'm watching eyes widen, maybe cause my likeness lowers expectations of tight rhyming. How would I know unless I'm rhyming in front of a bunch of blind men, dropping placebo-controlled science like I'm Richard Feynman?
Kevin Murphy, welcome to Learning Bayesian Statistics.
Thank you.
Yeah, thank you for taking the time. I'm super happy to have you on the show today. And I know a lot of listeners will be too, because a lot of listeners asked me for you to come on the show. So you see, folks, I do listen to you. Hopefully as often as you listen to me. So, yeah, like, without further ado, Kevin, I think a lot of listeners know you, but let's do that nonetheless. Like, can you define for us the work that you're doing nowadays and also the topics that you are particularly interested in?
Yeah, so I guess I'm interested in probabilistic modeling, machine learning, trying to extract structure from data and then use the sort of discovered structure to make predictions about the future or, decide on optimal actions. So, the core AI challenges, I think a lot of the success stories in recent years have been driven by deep learning that are sort of focusing on the data level. And, data is very powerful, but there are problem settings in which we don't have a lot of data. And then we need to sort of lean more on the model. Like, I think of it as like an iceberg, right? So you've got a lot of latent information hiding there. And I'm sort of interested in discovering that, which is useful for scientific purposes, but also it feels like if you could unlock the true data generating process, you could make much more powerful predictions and decision making than just working with superficial correlations.
Yeah. Well, I see where you're going with that. I'm not surprised you're on a Bayesian podcast. Okay, so perfect. I mean, that already sounds like very broad and very very fascinating. So can't wait to dive into all that. But in general, maybe let me ask you again a very broad question, but why do you think these topics that you're working on are important to study?
So I think, what I was saying earlier is if we look at deep learning, it's sort of, in some ways, they're structured models, like neural networks have layers in them, and there might be, convolutional layers or attention layers. But from a probabilistic point of view, it's just a mapping from X to Y, and it's relatively unstructured. So I think many listeners of this podcast more familiar with hierarchical Bayesian models, where it's like a very strong inductive bias that's created by hand, right? So they're structured probability models. If you think about the DAG that you draw, I think, NumPyro will visualize that using like GraphViz or something. And, Stan and so on, those libraries are all implicitly defining DAG. So they're structured probability models, but they're fairly rigid. So I think one of the things of interest to me is finding some sort of middle ground where we have structures that, ideally are discovered from the data. But, once you unlock some underlying pattern, whether it's a graph or a low-dimensional manifold, you can generalize much more easily, right, from this data. So it's all about, inverse probability, right? It's Bayesian, but, we can talk, if you like, about Bayesian ML. Yeah, Bayesian ML versus like Bayesian stats. That's like an interesting subtopic if you want to get into that.
Yeah, sure. I mean, we can get into that right now, actually. Because my next question would have been, why would Bayes be useful here? So, you already hinted at that. So if you want, you can answer that in particular, but then also make that distinction between Bayesian machine learning and Bayesian statistics, as you just mentioned.
Yeah, so I guess in statistics, often the goal is to uncover some structure in the data and then maybe to do hypothesis testing, right? Does this group have a higher rate of cancer than this other group or whatever? So there's sort of an assumption there's a human in the loop. The models are often fairly simple. They're designed to be interpretable, and you want to model uncertainty about latent parameters because the parameters might have some causal meaning. I think in machine learning, we don't really believe our models. It's much more focused on prediction. The models are usually unidentifiable. So focusing on uncertainty about parameter estimates is really just a means to an end. Like, we don't want to try and look at the probability distribution over weight 722 in my neural network with 1 million parameters, because that parameter is just some piece of a non-parametric function. So in machine learning, the focus is much more on predictive accuracy, and you can, in some settings, you will, like, particularly when you want to predict out of sample, then you're going to want to quantify your uncertainty there. And one good way to do that is, to pass the uncertainty about your parameters through into the predictive distribution. But you don't really care about the parameters themselves. So as a practical matter, most machine learning people just use point estimates because they only care about prediction. One of my pet peeves is, a lot of machine learning people will say, oh, that's frequentist because we're just doing a point estimate. But it's not frequentist statistics. They think, like, if you do MLE or map estimation, you're a frequentist. And if you compute the posterior, you're a Bayesian. But I think that's an incorrect characterization, right? If you just compute a point estimate, you could think of that as poor man's Bayes, which is like a computational shortcut. It's a very low quality approximation to the posterior, but it's very quick often to compute. But it's not really modeling uncertainty at all. So I wouldn't say that's a frequentist approach. It's just like poor man's Bayes in a way. It's like you don't care about uncertainty. The frequentist approach is, an entirely different philosophy, right, about repeated trials. And that shows up in other methods like cross-validation or conformal prediction, but it's not related to point estimation as such. I think that's a common misunderstanding.
Yeah, it's like that idea also of like basically repeatability of the experiments and things like that. Yeah. Okay, so cool, because indeed that point is important. And so you would say that you focus more on the Bayesian machine learning type of things or on the Bayesian stats, or that you do both?
I guess both. I'm sort of interested in the spectrum from one to the other. the Bayesian stats with sort of interpretable models. Well, most of my research is focused on probabilistic graphical models. That's what I did in my thesis. That's probably certainly my older work, which I'm most well known for. So they are structured probability models that, or used to be anyway, used in machine learning. So it's a way of essentially, you could take a sort of hierarchical Bayesian model that's used in, like a mixed effects model or something like classical, like that Bambi or one of these packages would implement. But they make pretty strong assumptions that each local conditional term is a linear model. Maybe it's, it might not be Gaussian, right? It might have a Poisson distribution or something, or some non-conjugate prior. But generally, the relationships are linear. In some cases, people are using splines and so on to get some more flexibility. But you can stick neural nets into any link in this graphical model, right? So that's one way to introduce sort of deep learning inside of a more classical model. The alternative is to say you have a classical model so that's what I would call, I want to distinguish Bayesian deep learning from deep Bayesian learning. So I guess Bayesian deep learning would be you would take like some neural net component and add it on top of your existing statistical model, perhaps to model low-level parts of the system, like the image generation or the sound generation that you don't have a good causal model or generative model for. And then the higher level parts of the model are more interpretable, and they're the things that you really care about inferring. So that's one approach. The alternative would be you write down your classical model, and it might be quite complicated. Maybe it's a spatial temporal model or something. It could be nonlinear. Maybe the nonlinearity is induced using GPs or something. So it's still sort of classical. And then you want to speed up inference, and it's a computational problem. And in that case, you can use neural networks as proposal distributions inside of, say, SMC or MTMC. And you can think of variational autoencoders that's like a combination of the two ideas. But you can use amortized inference methods where you use a neural network essentially as a proposal distribution to speed up computation, but it's not part of the model. So the model might be, a fairly interpretable, potentially even linear hierarchical model, but it's very large. And you're using neural nets for computational purposes. So that would be so there's BDL and DBL, deep Bayesian learning. So the deep is on the outside and the Bayesian learning is on the inside. So and of course you can put two and two together, right? So some listeners I'm sure will be familiar with variational autoencoders, which marry both of those ideas, right? The inference, the posterior inference is done with an inference network that's learned online. And then the generative model is itself a neural network, right? So it's got both things, but they're actually orthogonal ideas and you can mix and match.
Interesting. Yeah. Okay. Yeah. You can sky's the limit. Okay. Yeah. That's very interesting. And so we'll get back to that because lots of follow-up questions already. But I also wanna talk a bit about you because I love doing that, especially at the beginning of the show. Do you remember actually how you first got introduced to Bayesian methods? And you use them frequently, of course, nowadays. But also, why were they interesting to you?
Yeah, I mentioned graphical models already, so that's actually how I got started. I think it was in the late 90s, I guess, or mid 90s or something. I was at the Santa Fe Institute summer school, and David Heckerman, who at the time was a researcher at Microsoft, came to give a talk about graphical models. And he, at that time, in particular, directed graphical models, also called Bayes nets. And he was talking about, I don't remember exactly what he talked about. I think it was an entry-level talk saying, look, you can use these tools to find joint probability distributions, and you can infer anything from anything. And you just, condition on this node and assume it's observed, and then it will influence all the other nodes in the network. And unlike, say, a feed-forward neural network, you can run it backwards, you can run it forwards, you can do everything, right? And he had this demo, I think it was some medical example. This is sort of a canonical example where, you observe some symptom, maybe the person's coughing. So you say, okay, probability of cancer is, 0.3. And then you observe that that you condition on the event that they were exposed to someone with COVID last week. So you say, okay, cancer's not much less likely now and COVID's more likely. And then you discover that they're a smoker and you say, okay, none of these diseases are relevant now. Your beliefs about the explanations are going up and down, conditioning on the data. And it's all driven by this you have your model, which is this joint probability, which is easy to understand because you represent it as a sparse graph. And then you've got this inference algorithm that's doing all the computation. Now, these kinds of models in the AI community, at least in the 90s, and like Udapal's first book, right, was on this topic. These are usually assumed to be discrete random variables. And so the computation is either exact or oftentimes you can always do it exactly. It might just be too slow, but there are various methods you can use. So usually approaches based on message passing and so on. So not so much MCMC, you can use it there, but it's often unnecessary. So that was my entry into Bayes. And so this is not sort of Bayes stats like, linear regression. This is a different kind of Bayes where the uncertainty are over latent variables that generate the data that you see, but you're assuming that the parameters of the distributions are given to you or maybe estimated with MLE. But then you can just play the next move in the chess game and say, okay, well, my parameters are unknown as well. So you just add them as nodes to your graph, right? And this is exactly what you do in modeling languages like Stan and older ones like Bugs. So the parameters are random variables. They're just shared across all your data samples. And now the inference problem becomes harder because they're continuous random variables. You can't just sum out all possibilities. So you need to use, back then people were using Gibbs sampling a lot. And nowadays people tend to use HMC and variational inference. So that was my sort of entry. So in grad school, I was working on mostly these discrete graphical models and ways to solve the inference problem essentially by exploiting structure and various computer sciencey tricks. And then I started to sort of expand the scope and realize, okay, well, we need to do parameter learning as well. And then I was taking some stats classes at Berkeley, and obviously they focused on the frequentist tradition, and I found that quite confusing. So I was reading, I think DeGroot's book on the Bayesian approach, and it was just like, oh, this is so beautiful. And like closed form conjugate analysis is just, the math is so elegant, even though obviously from a modeling point of view, it's quite limiting. And these days, I think there's still a role for that these days as like a subroutine, because you can marginalize out certain parts of your model by leveraging these closed form solutions, right? So you don't have to sample your way through everything, which is often very slow. So that was a long answer to your question, but basically you're going to ask me about my history, I guess. Like I've listened to a few of your podcasts. I don't know when you'll ask me that question, but you can ask me why I was even at the Santa Fe Institute.
Yeah. So first, I'm flattered that you listen to some of the episodes. And indeed, but I pull a trick on you because, usually the background's the first question. But today I wanted to change and like dive directly into what you're doing nowadays. But indeed, that's my question now. It's like, can you tell us about your origin story and how you came to that world in the first place, and like how sinuous of a path it went?
Yeah, no, I was anticipating this question because I listened to a few of your podcasts when I'm walking my dog. So I know you have a formula. So I think of like several people of my generation, I got into AI because I read this book called Gödel, Escher, Bach, written by Douglas Hofstadter. That was, younger listeners may not have heard of it, but it's a great book. And I don't actually remember, I was thinking about this because I knew you'd ask me. I don't remember how I encountered that book. I think it was like a nerdy friend in high school. I grew up in England. Anyway, I read this book when I was a teenager, and it sort of opened my mind to just a lot of ideas. He was talking about AI, but like connecting it to intractability problems in math and philosophy. And it's a very eclectic book. It's a great read.
Yeah,
anyway,
sounds cool.
So then undergrad, I went to Cambridge for my undergrad. I didn't really get exposed to much AI. There really wasn't really any professors doing AI at the time then. There were some people doing speech recognition in the engineering department. So I had a little bit of exposure to that. But mostly I was doing functional programming and type theory. And that's kind of what Cambridge is known for. They're also known for computer science. At least this is in the 90s. They're also known as a very strong school for systems. But at the time, there's really not much AI or ML activity. I think more recently they've hired faculty in that area. But then I came to the US for graduate school, and I went to Penn for my master's degree. And Penn was known then and still is known as a very strong school for computational linguistics and natural language processing. But I didn't fall into that. I didn't go in that direction for various reasons. I got pulled into a slightly different direction, which is computational biology and modeling, DNA sequence alignment And there was a lot of buzz at the time about Human Genome Project and large-scale sequencing and trying to sort of discover patterns in all this data and maybe use it for curing diseases. So that was kind of interesting to me. And that a lot of the work in that field, at least at the time, was built on hidden Markov models and variations of that. So I started working on that kind of problem area. And then I decided to stay in the States for my PhD and then went to Berkeley. And then I took a class with Stuart Russell, who wrote like the AI textbook, because I was working on hidden Markov models and he was working on dynamic Bayes nets, which is like an extension of hidden Markov models to more structured domains where there's multiple random variables. That was pretty interesting to me. And then that's when I sort of had encountered the Heckerman talk and learned about graphical models. And I thought, okay, let's try to extend the library of tractable techniques to the temporal setting. So that was the topic of my thesis. And then I went to MIT for a postdoc. And I had been doing mostly sort of methods work in my PhD, but I was sort of always interested in applications. So I had basically most of my applications work has been either in like comp bio and computer vision. So when I went to MIT, I thought, okay, I want to do some vision work. So I started working with Antonio Torralba and Bill Freeman. And I remember this was actually a pretty fun project. I met Antonio Torralba. He's a very famous computer vision researcher. He's now a professor himself at MIT. And we were funded by DARPA and we had to make some demo. DARPA was going to come visit. And the goal was to do sort of real-time scene recognition and object recognition. And Antonio had this method for just computing very simple statistics of the image, basically like PCA on top of some image filtering outputs. And with that, you could like determine if you were indoors or outdoors or if what kind of room you're in. And that could be used as a contextual prior for the kinds of objects that you might detect. So it's like top-down inference, basically. And this is inspired by human vision, where there's a lot of top-down influence, and it makes things go much faster. So he was like classifying every frame separately. And then we were using object detectors biased by the output of the scene classifier. And it was very jerky. And I said, you could just stick an HMM on top and it would smooth everything out over time. And then you get temporal integration, right? Because if you're moving around, so we had to build this demo. I'll send you if I could find the photo, I'll send it to you. You can add it to the show notes. There's a crazy photo where we took a construction helmet and we drilled a hole in it and stuck a webcam in the hole of the helmet. So we could have a poor man's wearable computer system. And we walked around the MIT campus. We were running the code was all in MATLAB and it was running on a laptop, that we're carrying in our backpack. And it was doing real-time scene recognition. So this is when would this have been? 2004, so almost 10 years ago. So, the tools were quite different then. The laptops were heavier, the software wasn't as good. But we were able to do real-time place recognition and then on top of that, use that as like a signal to decide which kinds of object detectors to run. So if you're indoors, we turned off the car detector, right? And then you'd step outside and then it would recognize now you're outdoors, so there might be a car. So like you turn on your car detector and you turn off your water cooler detector or whatever. And I gave a talk on that at NeurIPS. At the time, it was called the NIPS conference. I think that was my own oral talk at NIPS. That was actually sort of an important event in my life because I was on the faculty job market. And so that got me some press at kind of just the right time. Then I moved to Canada at University of British Columbia in Vancouver. And I was there for almost 8 years, I guess. And I got tenure and they gave me a sabbatical as universities generously do. And I said, I'm going to go back to California, which is where I did my graduate work because I love California. And I was hearing all this buzz about Google being a great place to work. So I had many friends there. So I joined Google on my sabbatical and I really enjoyed the environment there and decided to stay. So I've been there for the last 10 years.
Nice. Yeah. And the rest is history.
Indeed.
And so the book you mentioned seemed interesting, so I'm going to read that. And that's Gödel, Escher, and Bach, right?
Exactly.
Okay. I'll put that in the show notes for people who are interested. Okay, cool. And so actually let's start diving a bit deeper with a very bad pun. So can you think of an example from your work or a project you had to illustrate, what you've been talking about, which is like what your work is, and also how Bayesian stats can be helpful in that regard?
Yeah, I guess, since I was just talking about the project with Antonio, I guess I could elaborate on that a little bit. I mean, this is older work. It's like 10 years old, but I think I still like it. And it's pretty simple. So I was talking about DAGs earlier, right? Like people who work in Stan and so on will be familiar with that. But you can imagine now that these random variables, at the top of if it's a tree, it's representing the scene context. Are you indoors or outdoors, whatever. And then below, you've got all these objects that may or may not be present in the scene. And there's visual evidence for that. But there's also, prior context, right? You wouldn't expect to see a car indoors. And so you can actually do message passing on that graphical model where you integrate information bottom up and top down. And then you can extend that over time. So you can basically build a you can combine tree structures with chain structures. And you get some, you might encounter some computational problems, but it's a very natural model for a lot of application domains. And you can think about, in general, I think one of the things I'm interested in back then and still am now is like online inference, sequential inference, which I think is somewhat understudied in the AI community. It's obviously, there is work on sequence modeling, but it's often offline, like a batch of data is processed offline. But when you're solving real-time control problems, if you're doing robotics or whatever, you have to do everything in real time. And so in that setting, you can work with state space models. And often the state spaces are kind of flat. It's just like one random vector. It might be high dimensional, but I think exploiting structure in that state space as it evolves over time is, I think a very interesting challenge. So, that stuff 10 years ago was a sort of simple special case of that, where we sort of learned all the pieces separately. But now, there's much more interest in end-to-end learning where you just, receive a stream of frames and you want to magically discover all the objects that generated those pixels. And that's very hard, but it's a good challenge to work on.
Yeah, definitely. And how would you say I'm interested also all the time in the difficulties that you encountered with this project and what you learned from them and like how it helped you maybe in projects that you work on maybe even today.
I was just realizing, I looked up on my webpage when that paper came out, the one that I was just discussing. So of course, 2004 is almost 20 years ago, not 10 years ago.
Right,
so,
indeed.
After that, I did, when I was in Vancouver, I mostly did comp bio stuff and focus on learning the structure of these graphs and more HMM stuff for RNA sequencing and so on. And then, at Google, I started doing some knowledge-based stuff and then some vision stuff. And now I'm sort of back into state-space models and online inference. But sorry, re-ask your question. What did you just ask me?
Yeah, and also this paper, if you can put it in the show notes, that's perfect.
Sure.
Yeah. So basically, I was curious in that project, which difficulties did you encounter, and what did you learn from them?
The main challenges are efficient inference. So, I mean, if you're a Bayesian, often the modeling questions relatively straightforward. I mean, there are certainly things we don't know how to model, and then we learn them from data, but usually our ideas run ahead of our ability to compute. So, like I said, I was, in the past more focused on discrete latent random variables, and nowadays, everyone focuses much more on continuous latent random variables because you can apply gradient-based methods to infer them, which is much more efficient. And it's more, it applies also to the parameter estimation setting. Although I do think there's a need for both. So I guess I was coding everything in MATLAB. I built this general BayesNet toolbox, which, at the time was quite popular for doing inference and parameter estimation in graphical models. More recently, even then, I think some of my students when I was at UBC were saying, you've got to switch to Python. So after I moved to Google, I was doing some C++ and a little bit of Python. But then for my more recent book, I switched entirely to Python. And now I'm building a new library, actually, which we can talk about later if you like, in JAX for state-space models. So it's kind of fun for me to revisit old friends like Kalman filtering and so on, but with new tools. So, doing it in Python, doing it in JAX and using gradient-based learning instead of EM. And, our inference methodologies have improved, right? But then that just, as soon as we have a faster algorithm, then we make our models more complicated, right? Or we make our data sets bigger. So we're always, it makes sense, right? You're always at the cutting edge of what you can afford to do computationally. But
you're always complaining that the algorithm is too slow because,
exactly.
It's an arms race.
Exactly.
Yeah. No. Okay. Super interesting. And actually, let's continue on that path. So this episode looks a bit to a garden of forking path for me.
Yes. I have a paper with that name, actually, from 2020, The Garden of Forking Paths.
Perfect.
We were working, it's a common metaphor, right? But we are interested in video forecasting, actually, like for pedestrians, which way they're going to move. And that's the title of our paper. But that's yet another digression. Let's go back to what you're going to ask.
Well, yeah, I mean, if it's a Bayesian analysis, I'm of course interested in that. But I was going to ask you about that new package that you were talking about for state models in JAX. Can you give us the elevator pitch?
Yeah, and I'll put a link to this in the show notes too. So this is it's very recent. It's work in progress. I'm developing it with Scott Lindemann, who's a professor at Stanford, and like half a dozen students, Google Summer of Code students. And basically, we're trying to implement a variety of models at corresponding inference algorithms, state space models. So we have code for hidden Markov models and linear Gaussian state space models. And we're adding support for non-Gaussian state space models. And of course, once you enter the nonlinear and or non-Gaussian world, then you open Pandora's box. So our primary focus right now is on deterministic approximate inference methods. So based on linearization, extended common filter, general Gaussian filtering, posterior linearization, these kinds of things. So these are quite fast. We do intend at some point to add support for Monte Carlo, but there's already good packages for that, at least for static offline problems. And, you'd want to do both. So you can use these deterministic methods that are often biased, but quite fast. You can use them as proposals inside of SMC or whatever. But, for many, certainly real-time applications or big data applications, a biased but fast approximation is all that you can do. And it's plenty sufficient. So, so that's what we're doing. And it's pretty exciting. I think there's several folks around working on this, but with libraries like JAX, the code is fairly close to the math, so it's really quite pleasant to write in that framework.
Yeah, and I mean, what I like here is that it's definitely kind of at the edge, as you said, of the technologies we have right now, of the algorithms, and I do see a lot of people interested in different kinds of filtering, as you just talked about, but it's notoriously hard to sample from, especially if you want to do that in a fully Bayesian perspective. So definitely knowing that people like you are working on that is really great, because that means like probably pretty soon we'll get some stuff that allow everybody to do that more efficiently. And definitely that's something that's going to unlock a lot of power in new analysis and allow us to complain about a new algorithm that's too slow. I love that. And by the way, is that work open source? Do you guys need help on GitHub? Would you like people to come and contribute? What's the state of the package?
Yeah, it's fully open source. Anyone is welcome to contribute or comment. It's still very much in flux. So if you're not sort of part of the core team, it might be a little difficult, but we will certainly welcome help. I think at some point, probably in about a month or so, I think the GSOC program officially ends. That's the Google Summer of Code. Mm-hmm. So we hope to have some sort of milestone release at that point, which will be semi-stable, and I'll tweet about it. So it might be worth waiting till after that. Yeah, I mean, where I want to go with this is to learn. I mean, there's many applications actually, but I think one of them is to online or sequential learning of, let's say, neural nets. Mm-hmm. Like everyone just does SGD right now, and they have their batch of data and they'll sweep over it multiple times. But, in principle, a single forwards pass with sequential Bayesian inference is all you need, right? And if you could do exact Bayesian updates at each step, then you would have the true posterior and you could throw your old data away. So it's perfect for streaming applications. So I just love to show that, we could actually, I want to say beat the deep learning people at their own game, but I think SGD is just a very simple algorithm, right? And it's not very statistically efficient because you're making tiny updates to your parameters based on the data. And in settings where data is scarce, because, it's like Bayesian optimization or active learning, or it's online learning, but the data is changing, so you don't get a lot from any given distribution, then it's precious. So maybe we spend a little bit more compute, but we use less data. I mean, there's a trade-off, like some problems are data rich. So, I think some of these massive deep generative models that people are fitting these days, either large language models or these large vision models, they're trained on the whole internet, right? So they actually don't make multiple passes over the data set because they can't. It's just too much data. So they're actually making a single pass. But effectively, the internet has a lot of repeated content. So they are seeing the same example or variations of the same example multiple times. And this is a problem, actually. Like sometimes there are extreme repetitions of certain text passages, where it's like cut and paste, and then the algorithm will latch onto that because it's trained by maximum likelihood. And all it will do is like spit out, the Declaration of Independence or something that occurs, thousands of times on all these different websites. So there are teams, there's a project at Google, and probably there are projects elsewhere where they've trying to de-bias the data in various ways. And one of them being just to make it more balanced. So you remove these like gross duplications. But that's a digression. The online inference setting is potentially more efficient. And I think the other reason I'm very interested in it is that it provides a way to tackle distribution shifts, which I think is one of the most important current open problems in machine learning, is that, we know that you can get great results with these deep models, but then they're quite fragile. So if things change, like the viewing angle of the camera changes, or someone speaks with a slightly funny accent, then, they can fail in pretty embarrassing ways. And maybe the average performance is still good, but the performance on certain subpopulations is quite bad. So, you could try to train a model that's robust to these perturbations, but that's difficult because the world can change in arbitrary ways. So the thing I'm pursuing right now, it's called sometimes test time adaptation. So you basically wait until the data arrives, and then you update your model quickly based on a small amount of new data so that you sort of fine tune it, but perhaps without labels. So that's one of my motivations for focusing on this online setting, is that, you can quickly change your model, at least pieces of your model, with a small amount of data, even if you've sort of learned most of the parameters offline on a large amount of data, and you can quickly adapt. And as the world changes, you're always like keeping track of it. And this is what people do in control theory and robotics, right? And they used to do this kind of thing in speech recognition back in the 80s before, neural nets took over everything. They would take HMMs and then they would fine tune a few of the parameters online. Like you would have to say, you would open up some speech recognition app like Dragon Dictate or something, and it would say, okay, please speak the numbers 1 to 10 or whatever. And it would tune the model to your voice. And then after a while, more recently, that has proved to be unnecessary because they could train on enough people that the neural net would learn to, essentially it's amortized, right? Amortized inference again. If you have enough data, if you've heard accents from all over the world, then in a sense, nothing is new. Like you've heard it all before, so you don't really need to train on the fly. But clearly, in many domains, you can't possibly see all the data in advance, right? You're not going to cover all possible modes of your distribution. So you need to be able to adapt on the fly. And so I think this is, in principle, Bayes lets you do that. You do online updates, at least of the things that you're most uncertain about. Maybe some things are frozen for computational reasons. There's not much posterior uncertainty about them, so you don't need to update them.
Yeah, okay. So I understand now. Hence the focus on filtering methods.
Exactly.
Mm-hmm. Yeah, cool. Is there a particular part of the library that you would need people's help on, or everything is helpful?
Yeah, everything's helpful. It's too... like I said, it's a lot in flux right now. I think it will become, you should ask me again in a month, where I hope we'll have sort of a stable first release. I do think once we get into the world of, let's say SMC, so we're building these deterministic, like for HMMs, it's all fine because everything's exact, right? But in the case of nonlinear, non-Gaussian state space models, there's many different approximate algorithms, expectation propagation, VI, posterior linearization, yada, yada. You can now use these as proposals for SMC. So I think we don't want to reinvent the wheel there. Like I think some sort of mashup between what we're doing and let's say what Blackjacks has, that would be great to get help from SMC experts on that. And then, even in SMC lands, it's not just the proposal distribution, right? It's also the target distribution that you might want to modify. So I know that, Scott Lindemann, several of his students are working on this topic. but I don't know if their code is public yet. But I think that's once you start sort of hybridizing these algorithms, there's many combinations to try, and it's gonna take a lot of effort by the community to cover these bases. And I think to do a comparison, like I don't think there is a universal best algorithm, right? But depending on various characteristics of the problem, right? The size of the model, the size of the data, how fast you need the result. Like obviously I've been talking about filtering, but if you can afford to wait, then smoothing will give you much better estimates. So if you're not in a real-time setting, then you should just wait until you collect as much data as you can and then do offline smoothing. So typically we have multiple constraints on our problem, and therefore we're going to need multiple solutions. So in machine learning, it's always like, I have the best algorithm. No, I mean, best by what criteria, right? Like there's an obsession with predictive accuracy, but in most problems, that's only one of many factors that you care about, right? Speed is another we've just been talking about a lot, but also like data efficiency, I hinted at earlier. So you want to adapt with only a small number of samples from some mean distribution. Interpretability might be a concern. So there's a lot of factors.
Yeah, for sure. Okay, super cool. Very excited to see that package come out now. And if we go to a bit of a broader question, I'm actually interested in your field. What would you think would be your field's biggest question right now? Basically, the one question that you'd like the answer to before you die, let's say.
Oh God, that's pretty morbid. Before I die, oh gosh.
Welcome to the philosophical part of the podcast.
I hope the answer to this question will come sooner than that. So distribution shift, I think, is part of it's related to causality, right? So I think of causality as essentially modeling distributions that are shifted by actions, by perturbations, right? Either created by the agent or, natural experiment, some other agent. So they're sort of two sides of the same coin, I think. And there's a lot of work on causal inference, including, DAG-based approaches, but, which we associate with Pearl and other folks. I think a big open question in that literature is what's called causal representation learning. So if your data is just a bag of images, right? I have pixels. What's my DAG, right? What are the nodes in my graph, right? They're not going to be individual pixels. That doesn't make any sense.
Yeah.
They're not going to be the hidden units of a neural network because, that's just a function of the pixels and they're equally meaningless, right? I fit, a variational autoencoder. Let's say I take a VQ VAE, vector quantized VAE, where I have like a bag, like say a spatial grid of discretized latent variables that generate the data. So now you could say, okay, they're my random variables in my DAG, but you've assumed that they're spatially arranged. Maybe you stick an MRF on top of them, but that's an unidentifiable model. It's not really clear they have any causal meaning. They're still just capturing correlation in the pixels. So I think it's a big open problem. There are people working on this. I know Yoshua Bengio's doing a lot of work in the space, Bernard Chilkopf, and other people, Francesco Locatello, and many more people I can't remember off the top of my head. So this is something I'd like to get more into. I haven't had time really. I've been busy with my book and that library I was telling you about. But I think that's sort of related to what we discussed at the beginning of the podcast, which is this sort of mashup between interpretable structured models and deep learning that is great at working with raw data. And how do we bridge that gap? You could say it's the signal to symbol problem, as it's called in philosophy. I think it's not exactly that. That's sort of saying that we have symbolic representations of the whole world, which, is clearly not true. We can, humans can and do create symbolic abstractions on the fly to solve tasks. And, and often, we can then talk about them in words and so on. But I think they're sort of almost like throwaway models, right? Like scientific models are structured and interpretable like that. I mean, they're not really throwaway, but we do use different models for different tasks, right? Arguably, there is no truth. There's just utility. So I think being able to, earlier I talked about updating a model on the fly given new data, but, more ambitiously, we could learn a new theory about a new domain, right? Like I don't know, what's a good example? I take on a new task, right? Like I learned to ski when I was a teenager and then I switched to snowboarding, right? So I have to adapt my model and it's like a new set of muscle skills. Presumably there's certainly no symbolic model in my head for that. It's much more lower level. But I think in scientific areas, I think it's maybe easier to think about like some new disease comes along and it's some like COVID or whatever. it's related. It's a novel virus, right? But it's clearly not completely de novo. It's related to previous ones. So what aspects of this virus are different from the previous viruses and what aspects are new? And how do we identify these things? How do humans discover that kind of stuff? Like, we can't really do that with our machines right now, at least not without a human in the loop. So that's sort of the grand AI challenge, I think, is to discover structure and theories from data and then test them by, designing experiments. And I think once we can have more automated closed loop experimental apparatus, so we have, robot labs basically, then maybe we scientists will also be put out of jobs, which is maybe not a good thing. But there's certainly a lot of routine lab techs doing, pipetting and so on. And that's going to get automated away. And the algorithms will collect the data. They'll, scan the microscope slides and read the test tube results. And if they can come up with, I think a reason to go beyond just, pattern recognition, low level with deep learning and come up with hypotheses, that you have to choose what to do next, right? And there are many possible experiments you can perform. So you want that to sort of guide your way through the search space. You want to have parsimonious models so there's a limited number of choices about what you should do next. And then the robot would plan the experiment and take the action and update its belief. So it's still sequential Bayes, but it's sequential Bayes in a very rich hypothesis space. So all the stuff I was talking about earlier with the library that we're building, these are boring hypothesis spaces, right? These are just like vectors in Rn or maybe, mixtures of subspaces. So they're quite generic, right? You can apply them to many problems, but they're, in principle, you could do online Bayesian inference over trees and graphs and grammars and, scientific phenomena, right? Rich causal. You could imagine not just causal models in the sense of DAGs, but look at real scientific simulators where they're dynamical processes, right? They're like a weather simulator or a simulator of, a virus life cycle, right? There's a lot of parts in that. There's uncertainty about all kinds of mechanisms as well as rate parameters and so on and so forth.
Yeah, fascinating. Time is running by, so I do want to talk about your books, because you're also famous for a series of books about the probabilistic machine learning. So, of course, we'll put all of that in the show notes for the listeners, but kind of a meta question, because it's, of course, something that I'm very sensitive to. Yeah, sensitive to, right? Or about. I always confuse the preposition in English.
Good question. What's the rest of your sentence?
So anyway, that's something I'm very interested in. Science education. Kind of a meta question is, what drew you to science education, and what are the most important skills that you're trying to instill in students with your book and just in general your pedagogical work?
Well, I was a professor at UBC, as I mentioned, and I was teaching classes in machine learning. This is in the mid-2000s. And at the time, I guess the two most widely used textbooks were Chris Bishop's book and the Friedman Hasty Tiptrani book, and they're both excellent books. But I felt like it was difficult to teach from two different books that had very different philosophy and different notation. And in some senses, I kind of wanted the union of the two. To give a simple example, in general, I would say I preferred Bishop's book. I mean, it's more Bayesian, it's more graphical modelly, it's more, it's a machine learning book, it's not a statistics book. But it didn't cover things like Sooooo, right? He had relevance vector machines, which is one approach, which is basically a sparse kernel machine where sparsity is induced using empirical Bayes. But, I think a more common method would be to just do L1 regularization, right? To do Sooooo. And that's convex. It's a lot easier to optimize. So that was in the Hasty book, but not in the Bishop book. So I started writing notes like a lot of professors do, that some mashup of those things. And then I added extra content that wasn't in either book, I think neither covered Kalman filtering, for example, that we just talked about at length, and other topics like graphical model structure learning and whatnot. So my notes started growing and growing. And then I thought, maybe I should just write a book and just glue my notes together, basically. So this is in the late 2000s it would be. So it sort of grew, it took on a life of its own. I actually have always enjoyed writing sort of expository material on scientific topics. I actually won a prize in high school for some science writing competition. I don't remember the topic, something about information technology and society or something. Anyway, so I've always had I think I'm good at it. I certainly enjoy it. Anyway, so my teaching notes grew into a book, and then that culminated in my first book, which came out in 2012, that I published just as I finished it during my sabbatical, and I submitted it like the day before I joined Google, because I figured they wouldn't really be interested in me writing books. And then I wanted to do something new. And then that came out and it was kind of popular and time went by. And then a few years ago, I thought, well, the field has changed a lot. The deep learning revolution happened. Nobody's using MATLAB anymore. New algorithms. It's not just deep learning, but, amortized inference that we talked about. And, the takeover of HMC replacing Gibbs sampling and new understanding about natural gradient methods and, lots of methodological developments in the fields that were interesting and were not really written down anywhere. And I thought, okay, it's time to make a new version of the book. So I started working on that about 4 years ago, I guess. And then that started growing and growing and growing. And basically MIT Press said, okay, it's getting too big. You need to split it. So I ended up having what I call my introductory book, like book 1, that was published, I think, earlier this year. That's available in hard copy. And I just finished what I call book 2, my advanced topics book. I actually submitted the camera ready yesterday. I tweeted it on July 29th, and that was my first official launch. It's been up, a draft has been on the web for several months now. But the July 29th version was supposed to be the official one. I sent it to MIT Press, and then I went on holiday to Hawaii. And then when I was away on holiday, they found some errors, like some typos in people's names. And I had actually accidentally omitted a whole chapter from the table of contents. So there's always errors. I'm still fixing errors in my first book. But some of these were, they were easy to fix. So I just fixed those errors and made a few other tweaks and submitted the final camera ready version yesterday. So that will come out in paper form next year sometime. But it's already available online. And I'm pretty happy with that. Like basically, I think it's gotten some good feedback. I had like 4,000 likes on Twitter and various people have said nice things about it. I'm trying to, you asked me what the point was. So I'm trying to sort of convey the big picture about how all these things interrelate. So I mentioned earlier about, Bayesian deep learning and deep Bayesian learning and how they're not two sides of the same coin. They're orthogonal ideas, right? So we can write probability models and they can be linear or nonlinear. And I think of deep learning as basically, nonlinear function learning or nonlinear probability modeling. And, you can do amazing things like that, right? Making high resolution images and speech recognition and translation and, dialogue and just amazing stuff, right? And then there's the other side, which is building more interpretable models, maybe the hierarchical linear models, which is obviously super popular in applied statistics. But there could be also scientific simulations. We were talking a little bit about that earlier. And maybe you want to make those go fast so you can use neural nets in there. So there really was no book that sort of conveyed, I would say, the trees for the wood, right? So that painted the big picture and how all these things interrelate. So that was my goal. I don't know if I've succeeded in that goal, but I certainly cover a lot of ground in 1,300 pages.
Yeah, definitely. And I encourage, of course, listeners to check those out. And thank you for taking the time and writing those books, because I know that takes really a lot of time. So really congrats on that. I don't know how you managed to do all that.
No, it was a labor of love. It became, initially Google let you do these 20% projects and then it sort of grew to 40% and then 60%. And then my manager at one point said, look, just screw it, just finish the freaking book and then get back to your day job. So even if I had to, so it sort of became, and towards the end, it was like, effectively my full-time job. But I had help from some excellent co-authors who are listed on the webpage, too many to name right now. But during COVID, that was my decision. I put the book on hold during COVID to help out with a couple of COVID projects. And then I realized, when I finished those COVID projects and I thought, okay, I still have this mountain to climb and I really want to get it done. And I said, okay, it's just too much work for one person. So I reached out to colleagues and I have various guest authors who've written various chapters, and that really helps finish it in a reasonable timeline.
Yeah. Well done. That's super cool to have these very important books out there, and I'm sure it's gonna drive some of your points home. Hopefully, this podcast is also helping. And actually, you told me before the show that it's your first podcast, so how honored am I? And hopefully that will also help you reach new audiences, because some people prefer audio format, some people prefer writing format. So thank you for innovating your way of communication with me.
Oh, you're welcome. Yeah, one of my colleagues actually who helped with the book, Mahmoud Solomon, he said he never reads, he always does stuff on YouTube. He said I should have a YouTube channel, but maybe that will be next. But yeah, I think there's multimedia, right? Paper is good for some things, particularly for math. But I think for high-level ideas, podcasts and videos are great.
Yeah. And also it depends on what you enjoy. I know that I enjoy the podcast format way more than the writing format personally. So, it's also like a question of like how your personal style of communication is, I guess. So actually, I realized that I don't have your Twitter account in the show notes. So make sure to put that in. So before asking you the last question, I still have a couple hopefully short questions. But yeah, talking about that communication thing and the different media that you can use, I'm curious, like, who you think is interested in what you're saying or in what you're writing, but also who you would like to be interested in what you're saying and writing.
If I look at the GitHub issue, I don't have any metrics on who downloads my book, so I actually don't even know. Let me look what the download counts are. When I first published it, I do this. My wife would say it's just me fluffing my vanity, but now, whatever, it's popular. People download it. The latest, I'm mostly talking about what I call book 2, my advanced copy. So 64,000 downloads. That's pretty nice since February this year. So in like 6 months. So it's not selling like hotcakes, but downloading like hotcakes. So I don't know who these people are. I'd love to know. The only insight I have is from GitHub issues. And so sometimes people, find typos. I'm sure you'll find typos. I encourage all readers to read the book and make open issues with any errors that they find. And I'll fix the online version. Anyway, so sometimes I click on the name and you can't always tell with GitHub, right, anything about the person, but in some cases you can. So it seems to be an equal mix of like students and industry people, certainly for book 1, I guess, which is more elementary and more applied. I suppose the second book is more focused on researchers. So in some ways, I'll sound like an old cranky guy now, but like in some ways, I think, the kids these days, they don't, it's not that they've forgotten the classics of the past. They just don't know them. Like very few, I don't know if anyone teaching machine learning these days, or very few people, I think, cover the classic topics like, Kalman filtering, extended Kalman filtering, and even sequential Bayes, right? Like most people don't know about that. And then like belief propagation and the fact that there are optimal solutions to various subproblems, right? Which you can combine with deep learning, right? It's not all deep learning. This gets my point. Like I think in some ways, the algorithmic toolbox in deep learning is not that interesting, right? You can innovate by changing the wiring diagram, although you can automate that with neural architecture search. And then you just write down an objective and fit it with SGD. And then maybe the objective is like supervised loss, but maybe it's like some self-supervised thing where you mask parts of the input and you try to predict it. And I don't know, like algorithmically or methodologically, it's not that interesting, I think. I think there are other parts of machine learning where there's more creativity, I would say, in terms of the methods and the math. And some of that's still alive, I think, certainly alive in the causality space and people working identifiability. I think in the state-space modeling world, there's maybe still, interesting. There's definitely still innovative methodological work going on, not going to deny it. But I think it's not, some of that's on the fringes, and I think it's sort of often dismissed as, there's no neural net in there. It can't possibly be interesting or useful. And so I'm trying to somewhat overcome that bias. Yeah. And particularly, I would say one more thing. I know we're almost out of time, but now we're in an era of big pre-trained models, right? Which, if you're working on image or text data, you could just download some model off the web and it will create an embedding for you that's pretty good low-dimensional representation of your data. And that actually, I think, now allows those of us who like working with, Bayesian models and maybe small-scale experiments you can just run on your laptop. You could do that in the past. And then the deep learning guys came along and sort of swept the floor because they had much better results with big models and big data. But now those models are so big, you can't afford to train them. So you just take them off the shelf. And now you can use their outputs, their embeddings as features. And now you can go back to doing sort of fancy modeling that maybe hierarchical Bayes or online Bayes or whatever it is, right? Whatever your favorite tool is. And you'll actually get good empirical results because a lot of the low-level feature extraction has been done for you. And now you can focus on higher level things, like the things that are related to actions you perform or interpretability or whatever it is, right? So I think we will be able to, some of those old tools will start to become much more practical when used in conjunction with modern deep learning.
Mm-hmm. Yeah. Exciting. Okay, Kevin, unfortunately, I have many more questions, but we'll have to stop there. Let me ask you very fast the last two questions. Of course, I ask every guest at the end of the show, you know that. So first one, if you had unlimited time and resources, which problem would you try to solve?
Yeah, I mean, I think technically I would like to spend more cycles learning about and working on causality and causal representation learning and its connection to distribution shift. I mean, I am looking into some of those things right now. I think, as a societal problem, I know a lot of your guests have said climate change. I mean, clearly it's like one of the biggest problems for humanity right now. I think, realistically speaking, behavior change is hard. People are not going to turn off the air conditioning or stop eating meat. I think as technologists, I think the only solution is technology. Maybe it's carbon capture. Maybe it's just cheaper electricity. I think we need to fight on multiple fronts. I think, evangelizing about the benefits of not eating meat, I think would actually move the needle, electric cars, whatever, all of these things, we have to do all of them. But I think maybe, I don't think like AI is going to cure, solve climate problems, right? But I think if we build, I'm certainly not a domain expert on that stuff, right? But I think if the machine learning AI community builds reliable tools, particularly, the computational Bayesian stats community, like by building faster inference libraries, we can empower domain experts, like, real climatologists, people who know what they're talking about, people who, model the effect of aerosols on solar radiation or whatever, right? Or on health. We can focus on the algorithms, make them efficient, make high quality code that will enable domain experts to hopefully, achieve, 10x improvement or maybe some even more radical breakthrough, right? Like, just like we saw with the vaccines for COVID, right? Like, technology can do amazing things. And, we can nudge people to wear masks and socially distant, but it makes some difference on the edge. But it was really vaccines that moved the needle, right? And I think for climate change, we've got to have just radical breakthroughs, like, safe nuclear fusion or, a way more efficient alternative energy or, really tasty alternatives to meat, which people are developing, whatever, right? All of these things. So it'll be great I'd love for the things I'm doing to sort of be influential or helpful there. That'd be fantastic.
Yeah. Love that answer. Awesome. And so last question, if you could have dinner with any great scientific mind, dead, alive, or fictional, who would it be? I
was thinking about this. So I've listened to a few of your podcasts and a lot of your guests pick, very famous people like, von Neumann or Turing or Reverend Bayes or whatever, right? Yeah. And they would be all great, right? But I feel like in reality, I wouldn't have much to talk about with those people. There's just too much of a distribution shift between someone who lived in the 18th century and now, right? Like, so this is a very personal answer, but I would pick Sam Roes. So he probably won't be known to many of your listeners, but you can Google him later. He unfortunately passed away. I think it was in 2010 or thereabouts. But he was a friend of mine. He was a great scientist, machine learning guy. He was a professor at NYU. And he did a lot of work on latent variable modeling and embedding, probabilistic modeling, and its sort of interface with neural modeling. And he was such a creative and fun guy to be with. I used to go skiing with him at the NIPS conference, and we used to hang out together at this Canadian workshop that Jeff Hinton was running. And I think it was a real loss to the community and obviously to his family when he passed. But I think so I would enjoy, having more time with him. I know other people would too, but I think he would also, I just sort of wonder, what would Sam think about recent developments in deep learning, right? Would he, what would he do? Because I think he had great taste in problems. And, in some ways I feel a lot of people feel pressure to, they've got to get a method that's winning some benchmark, or they have to have, 5 papers published every year. But I think the people I like hanging out with are the ones that, have taste in the problems that they work on, and they like elegant solutions, right? Elegant solutions that work, right? It's not just mathematical masturbation. That's my advice to use to call it. But that if you can find something that's mathematically elegant and actually works in practice, that is like, 100x more efficient, yeah, that's sort of the dream, right? You get the best of both worlds.
Okay, so Kevin, awesome. Thanks again for taking the time and be on the show. That's awesome. I learned so much and could have asked you about many more things, but that will be for another time. Congrats again on the books. As usual, I put resources and a link to your website and Twitter in the show notes for those who want to dig deeper. Thank you again, Kevin, for taking the time and being on this show.
Thanks for inviting me.
This has been another episode of Learning Bayesian Statistics. Be sure to rate, review, and subscribe to the show on your favorite podcatcher or on Podchaser, and visit learnbayesstats.com for more resources based on today's topics, as well as access to more episodes that will help you reach true Bayesian state of mind. That's learnbayesstats.com. Our theme music is Good Bayesian by Baba Brinkman with MC Lars and Megaran. Check out his awesome work at bababrinkman.com. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. You can support the show and unlock exclusive benefits by visiting patreon.com/learnbayesstats. Thanks so much for listening and for your support. You're truly a
good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. Let me show you how to be a good Bayesian. Change calculations after taking fresh data in. Those predictions that your brain is making, let's get them on a solid foundation.